leave the word to our next speaker, Riccardo.
Yes, do you hear me?
Yes, I can hear you. You can share your screen.
Yes. Do you see slides?
Yeah, I know that place.
It's nice.
Riccardo is now at EPFL, right?
Yes.
And, okay, as a PhD student, I guess.
Yes.
Okay, and today is going to talk about PDE-aware deep learning for inverse problems in cardiac electrophysiology. Just before starting, Riccardo, the slide is a bit cut in the bottom, maybe.
Is a little bit cut?
Yeah.
Is it? Okay.
You can either use the full screen mode.
Yeah, I am in full screen mode actually.
Okay, because
is it still cut?
Yeah, in my opinion, yes, because for instance, the bottom part in red with your name, PFL and something else, I mean, is not visible at the moment on the screen.
Okay.
Actually, we don't see them in full screen mode.
Yeah.
We see it in the viewers mode.
Okay, so I can try to share the whole screen. I just share the app. So it's better now?
Yeah, great.
Okay,
Now it's
so yeah, it was okay. Sorry.
You can start.
Okay, so first of all, good afternoon to everyone, and thank you for this opportunity of giving this talk. Very happy to do this. So yeah, as Andrea told, today we'll speak about PDE-aware deep learning for inverse problems in cardiac electrophysiology, which actually some months ago has been my master thesis. And I work with it together with Stefano Pagani and Dalcio Quarteroni, which are from Politecnico di Milano, and also with Professor Simone De Paris at the EPFL, which is currently my PhD advisor as well. So the goal of the project is to approximate the epicardial electrical activity from recordings of the body surface potentials. And this kind of goal, this kind of task is on the one side challenging, but on the other side is also very appealing. So the reason why it is appealing is that epicardial electrical activity, let's say cardiac potentials, epicardial potentials, nowadays can be measured only by invasive and intrusive measurement techniques, which are time-consuming and which also are of higher risk from the point of view of the patient, while body surface potentials can be measured very easily in a fast and economical way just by placing electrodes on the patient's skin. So the perspective of reconstructing something that is difficult and challenging to be measured by measuring something which can be measured very easily is for sure something appealing. But as everything that is appealing is also challenging in some way. And the reason why this is challenging is that the problem is ill-posed because it's an inverse problem actually. So what happens is that if you want the electric signal propagates from the heart, from the epicardium, through the torso and the different organs inside the human torso until the body surface. And it sort of follows a diffusion process. Indeed, this is modeled via a generalized Laplace equation, so a Laplacian second-order differential equation. But here we have to solve it in the other way around. So we know the potentials on the body surface, and we have to reconstruct what happens on the epicardium. So it is an inverse problem, which by nature it is ill-posed, and that's why classical methods to solve it, which rely on a minimization of a suitable functional, rely on stabilization and regularization techniques. What we have tried to do, what we want to do instead is to sort of modify a little bit the approach and be aware of the physics of the problem, be aware of the physical laws that govern the phenomenon at hand, but also use the power of data. So you all know that we are in big data era, we are in the machine learning era in some sense. And so we want to combine the two approaches, so develop a hybrid model, which is both data-driven and physics-aware to carry out this task. So at a glimpse, what we have is that we have some body surface potentials, which are provided an input to the model. In this case, we have just simple 12-lead ECG signals. The model processes these signals, and the model is made aware somehow of the physics of the problem expressed by means of PDEs. And in the end, we try to reconstruct the epicardial electrical activity, which here is represented in the form of an epicardial activation map. And here, for instance, we clearly see an epicardial breakthrough, which is a point where the signal comes out to the epicardium and then diffuses over the whole epicardial surface. So the very first problem we encountered, which is a challenging problem, is again data generation, because the amount of clinical data regarding epicardial potentials and cardiac potentials in general is very reduced. So in our setting, we are not actually in a big data regime, but we are in a small data regime, which kind of justifies why we want to use physics. Because if you don't have enough data, machine learning alone is not typically enough, and you have to enrich the knowledge of the model with something else, which is physics in this case. So what we have decided to do to overcome the problem of data is to test and to train and test our model using in silico data. So data have been generated numerically. For the cardiac electrophysiology, we have used the B-domain equations coupled with a fairly simple phenomenological ionic model, which is the famous Alex Pamphilov ionic model. While the problem in the torso, the so-called forward problem of electrocardiography, has been modeled by a generalized Laplace equation, which is the fourth equation in red reported in this box. And as an additional assumption, we have decided to work under the isolated art assumption, meaning that there is just a one-way coupling between the cardiac electrophysiology and the forward problem of electrocardiography. So the boundary conditions for the cardiac electrophysiology problem are just homogeneous Neumann boundary conditions for both the intracellular and the extracellular potentials, which are the two potentials that represent the variables, the unknowns in the B-domain, the formulation of the B-domain equations. While when solving the forward problem of electrocardiography, we have just imposed the torso potential UT to be equal to the epicardial extracellular potential on top of the epicardial surface. So basically, we have sort of fully decoupled the two problems, and this allowed us to first solve cardiac electrophysiology and then solve the forward problem of electrocardiography and generate the data set in a much faster and less computationally expensive way. These are some other details about the full of the model simulation. So we took into account an isotopy of the cardiac tissue, so the fact that there are conducting fibers along which the signal propagates faster. There is transmural heterogeneity, so the propagation of the signal is actually faster in the endocardium and actually in the mid-myocardium rather than in the epicardium. We have a zero average constraint on the epicardial extracellular potential. We have used semi-implicit first-order time marching scheme for the time advancing and preconditioned BGG-style iterative solver to solve the linear systems arising from the discretization of cardiac electrophysiology. So here is actually the model we have implemented, which is called space-time reduced basis deep neural network model. So the model takes as input body surface signals, as you can see, body surface signals which can be rough time series signals, but that can also be sort of quantities that are computed from body surface signals, as for instance, discrete Fourier transform coefficients, as you will see in a while. The signals, so whichever quantities computed from the signals, are then processed by a first part of the network, which we call the trainable encoder. It's trainable because it's actually a trainable neural network characterized by a set of weights and biases. Here we have represented by this theta in this image. And it is the encoder because this neural network encodes the information coming from the body surface signals into estimating sort of two types of quantities. So the first type of quantity is here reported in orange, and this UE. And so this is actually the epicardial extracellular potential. So it's the potential that is measured on the epicardial surface, but the potential is not estimated as projected onto the full of the model space, say in a finite element space, because we have used a quite a refined mesh for the art. Then the problem is time dependent. Thus, that would mean estimating millions or even billions of coefficients. And this is not feasible. The network is very likely not to learn so many coefficients. And even if the network manages to learn them, then it is very likely that the network cannot be trained, if not on supercomputers, let's say. So what we have decided to do is to estimate the epicardial extracellular potential as projected onto a space-time reduced subspace, which has been generated from the same set of data that are actually present in the training dataset. So the training dataset is used both as training dataset, so to train the model, and also to build this space-time reduced subspace, which is generated according to the space-time reduced basis method, so via proper orthogonal decompositions of snapshots, basically. Then this potential is actually rescaled suitably and returned in output. So it's one output of the network, but then the network is also composed of a second part, which is here reported in cyan. So this part is actually a deterministic space-only reduced basis solver for the forward problem of electrocardiography, which takes as input the epicardial extracellular potential, which acts as a boundary condition, as we have seen before, and also this mu tilde A, which are coefficients that sort of influence the propagation of the signal to the torso. For instance, they could be the electrical conductivities of the different organs that are present in the torso. So then the decoder, the CN part, is not trainable, it's purely deterministic, and using the reduced basis method, it solves the forward problem of electrocardiography, and it reconstructs in output the alter ego of the same signals provided in input, but using the epicardial potential, which has been predicted by the network. So in the end, the loss is the weighted average between the estimation error, which is made on the body surface signals, and the error that is made, which is measured with the MSE, and the error, which is instead measured with the MAE weighted by the singular values arising from the space-time reduced basis, that is committed on the epicardial extracellular potential, plus a regularization term, which together with dropout layers allows to reduce the effect of overfitting. So in the end, this model is and features two elements of physical awareness. So on the one side, we have that the epicardial extracellular potential is predicted as projected onto a space-time reduced space generated from solutions to the cardiac electrophysiology. So it's sort of constrained to belong to a space spanned by solution to the problem. And the second is that as we penalize body surface signals generated by the epicardial extracellular potential, the epicardial extracellular potential that we predict must give rise to body surface signals, which are as close as possible to the target ones. So in detail, we have developed two versions of this model. One takes as input time series signals, so it's called the time series based model. And in this case, the trainable neural network is a 1D convolutional neural network, which convolves signals over time to sort of exploit their temporal dynamics. While the second model is the DFT-based model, where the input of the model are the real and imaginary parts of the lowest frequency DFT coefficients computed from body surface signals. And as the DFT, discrete Fourier transform, already takes into account temporal dynamics, in this case, the neural network is no longer a convolutional one, but is just a multiple layer perceptron, so several flanked, fully connected layers. Briefly, the test case. So the data set we used is made of 400 different data points, which have been generated solving cardiac electrophysiology and the forward problem of electrocardiography, varying some characteristic parameters, as the parameters of the Aleph-Pamphilov ionic model or the electrical conductivities longitudinally and transversally to the conductive fibers, and also other parameters that characterize our models. We have built up two different data sets, actually, one where the input signals are just 12 signals, the classical 12-lead ECGs, and another where instead we have 158 signals recorded by 155 electrodes, and this sort of mimics so a sort of vest of electrodes, which is used in modern SCGI applications. And we have compared the performances of the time series based and the DFT-based models using both type of inputs, using as an evaluation metric the L1 norm relative error on the epicardial activation maps. So these are the results that we have obtained for the time series based model. The images refer to one single data point that refers in particular to an LT patient in this case. This data point is was proved to be sort of a simple one. So it's one where both models, actually also the DFT one, showed best performances. And indeed, we see that we've compared the first column, which is the reduced to the modeling approximation, with the second and the third. We see that all the epicardial breakthroughs, so the regions where the signal comes out, are well detected, both spatially and temporally. And in the tables, we see the errors. In this case, the errors do not refer to this data point, but they are averaged over all the 40 data points that we have used for testing. And we see that the relative error on activation maps is of the order of 4%, but we do not get better if we give to the model more signals. The models have more or less the same behavior. Conversely, if we consider the DFT-based model, well, here we see, first of all, that the average errors that we obtain on the test are smaller. So we are 3.5% with 12 signals in input, and 3.3% if we have 1.58 signals in input. So we have we get better of 0.2%. So why do we get better qualitatively, let's say? Well, it's well depicted here. So if we see the model that takes as input 12-lead ECG signal predicts an epicardial breakthrough at about 20 milliseconds in the inferolateral portion of the left ventricle. This epicardial breakthrough is actually not present in the reduced to the modeling approximation, and it is no longer estimated if we give as input to the model more signals. So for the DFT-based model, we sort of seen that giving more signals in input allowed to better identify epicardial breakthroughs and either identify epicardial breakthroughs that were not identified before or not identify epicardial breakthroughs that were instead identified, giving less signals in input. Yeah, so this is the reconstruction of the body surface signals, which proved to be quite accurate for both models. And so to conclude, we managed to build PDE-aware deep learning models that allow to get fast and good reconstruction of the epicardial activation maps, epicardial electrical activity, with a low computational costs. The errors, as we have seen, are of the order of 3–4%, and the training of the models just took 10 minutes. Obviously, in terms of further developments, what we have done for the moment is sort of a proof of concept, if you want. So we have moved in a very simplistic framework. What we want to do is to try to bridge the gap with clinical applications, is to move to a more realistic settings. So build a more realistic and heterogeneous data set, which, for instance, takes into account the presence of different organs inside the torso that we have not done for the moment, which takes into account patient geometry variability, so different geometries for the torso, for the heart, and rotations of the heart within the torso, and also takes into account a more realistic modelization of noise. For the moment, we've just used correlated white Gaussian noise, while we know that body surface signals exhibit sources of noise which are different and more complex, but there's literature about that, and so it's in the plans to also take into account that. So I thank you for your attention, and I'm open for questions.
Thanks to you, Riccardo. So the floor is open for questions. So unmute yourself or raise your hands if you have questions or comments for Riccardo. Luca.
Thank you, Riccardo. There is something that I don't understand. I'm starting from the very end. And in the future developments, you are saying that you want to parameterize the heart and the torso geometries. But if I remember correctly, from the very beginning of your talk, basically you are relating a field over the heart surface to measurement of the potential on the body, right, across the torso. And then you establish this link by using the neural network and so on. So you don't have any model for the torso, right? A physical model based for the torso. But then in the future development, if I understand correctly, you plan to put into place also information, for example, parameterized position, rotation of the heart in the torso. So how is coming into place this parameterization? And if this parameterization is in need of a physical based model for electrophysiology, for the electrophysiology of the torso. Thank you.
So yeah, very nice question. Thank you, Luca. So what I'm referring here when I'm speaking about parameterized heart and torso geometry, so all the further developments basically refers to the generation of the data set, because we have used data that have been generated in silico, as we have said, solving numerical simulations for cardiac electrophysiology and the forward problem of electrocardiography. And the point is that for the moment, all the data that we have generated have been generated using a fixed heart geometry, which is actually just a biventricular geometry, is not a full heart geometry, and the fixed torso geometry. But the literature has proved that varying the geometry of the torso, the positions of the organs inside the torso, the rotation of the heart within the torso, changes a lot, or changes somehow body surface signals, changing ECG signals. So the idea would be to build up a data set which is more heterogeneous, where we solve the problem, the electrophysiology problem in different geometries, in order to, increase the data set and increase the variability inside the data set. Then the point is that it would be also interesting that the neural network, other than estimating the epicardial potential and the conductivities of the parameters of the different organs present inside the torso, also would estimate parameters that relate to the geometry. So we give as input to the neural network body surface signals, and the neural network estimates on the one side the epicardial potential, on the other side the conductivity of the organs inside the torso, and on the other side some parameters that tell us how the heart is oriented, for instance, within the torso. So this kind of further development refers to the data generation stage, not to the training or the testing of the neural network itself.
Thank you, Riccardo. But would it be possible to put add as parameters these parameters to the network? So I mean, a parameterized, let's say you parameterize the position or rotation of the heart in the torso, and you add them as inputs of your network all together with the, let's say, the electric information that is feeding the current network.
Yeah, that's another possibility. I mean, geometric parameters, sorry, can be used both as an input or as, let's say, a byproduct of the network, if you want. I mean, they are estimated by a network, but they're not involved in the loss functional. Obviously, giving them as input to the model means that in actual clinical practice, you need to recover such parameters sort of from imaging. So if the final idea is to sort of elaborate something that at clinical level works as you put signals in input to the network and you get information from the epicardial potentials, then maybe at clinical level, you don't have information about the geometrical parameters. So that's the reason why for the moment we have imagined them more as a byproduct of the network together with the electrical conductivities of the organs than as an input. But if these parameters were known, for instance, just staying on the in silico simulations, then yes, it would be also nice and interesting to see if giving them as input to the network would ameliorate the prediction performances, yes.
All right.